Okay, so as usual, please remember to type your name into the chat starting now, so that we have the record for your attendance, so we can continue to give you data. Um, welcome to everybody. It seems like people had some internet problems. That's okay. Hopefully, more people will come in over the next few minutes. We're going to do a topic today that I think should be pretty interesting. We're going to talk about a particular type of differential equation, which is called exponential growth and decay. And we're going to see how this has, lots of applications in physics, in biology, in economics, and also, well, we'll actually do two physics applications, one with radioactivity and one with Newton's law of heating and cooling. Okay, so it'll be a very applied class today. We'll start with a few formulas, but then mostly we'll get into applied problems. Okay, but before we do that, I want to go over the probability stuff that we did last time, just to review it and refresh it. Although today we're not going to be doing a lot of integration, so the probability will be integration. Today we're kind of going back to differentiation. All right, but first let's just do a little review from last time. So last time we talked about these probability density functions. And what was a probability density function? It was a function f on the real numbers, and it had to satisfy two properties. Okay, so the first property, sorry, Francis. Hi.
Hello,
Hello, Francis. How are you?
I'm good. How's
Good, good. I'm doing good. Thanks.
thank God.
Okay. So, no, Sunday. Okay, hold on. We're getting more people coming in. Okay, good time to come in because I'm just starting the review now. Okay. So, oh wait, more people admitting. Okay. Okay. So what's a probability density function? It has these two properties. So the first one is that it's always positive. It's always at least zero. And the second one is this strange thing, this integral from minus infinity to infinity. Remember what that means. It just means the total area under the curve. That the total area under the curve has to be 1, right? That's this intuition. The total area under the curve y equals f of x is 1. And what happens is this f of x is supposed to model some event that can take a range of values, like a temperature or a height or something like that. And if it models a random variable, then the probability that that variable takes a value between a and b is supposed to be the area under the curve f of x between a and b. So the picture here, right, is if I have a probability density function that looks something like this. So if this is my probability density function, y equals f of x, then the total area is equal to 1 under the curve. And then if I have 2 points A and B, then if I look at this area here, which is some proportion of 1, is the probability that the event takes a value between A and B. Okay, remember we talked about this discrete versus continuous last time. The probability that you take on any one particular value is always 0, but the probability that you take on some value inside a range from A to B, this is some number between 0 and 1. Okay. And we did a few examples of this last time. We talked about a uniform distribution. We talked about what was called an exponential distribution, about the length of time that a light bulb lives. And then in the end, we talked about this normal distribution, this bell curve. Okay, but in general, for anything that takes on a range of values and not discrete values, but it can be any real number in some range, then you have a probability density function, which tells you how you calculate the probability that you take a value between A and B. All that you do is you integrate the function from A to B, which, as we've seen, is the same as finding the area under the curve between A and B. Okay, so this is how we did probability density functions. So there's some homework exercises, right? So the first homework exercise was suppose we have this function. F of x is equal to 30 times x squared times 1 minus x squared between 0 and 1, and then it's 0 everywhere else. So what this means is that this random variable, it takes values only between 0 and 1. It can't take a value outside of 0, less than 0 or greater than 1, because the probability density function is 0 there, right? So maybe I'll actually just graph this on the computer just to see what it looks like. Graph y equals 30x squared, 1 minus x squared. I see a graph of this. Will it come? Okay, good, 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 good. Okay, so this graph more or less looks like this. I'll just show you what it looks like. Well, it's going to be 0. It's going to hit a peak here at 1/2, and it's going to go over here. So this is 1, and this is 0. This is what this graph looks like. This is y equals 30x squared, 1 minus x squared. Well, maybe I'll just say this is y equals f of x. Okay, I just did the graph on a graphing calculator. Okay. So the first question is if this represents a random variable x, what is the probability that x is greater than or equal to 1/2? Okay. So that probability means we've got this total area is equal to 1, right? This is we know this because it's a probability density function. So this total area is equal to 1. So I want to know what proportion of that area is greater than 1/2, right? So I'm really looking at this proportion of the area, and I want to know what's the probability that x is greater than 1/2, right? So really what I'm trying to calculate is the integral from 1/2 to infinity of f of x dx, right? This is the total area under the curve to the right of 1/2, bigger than 1/2. But we also know that this function f of x is just 0 when x is greater than 1, right? So you can write this as the integral from 1/2 to 1 of f of x dx plus the integral from 1 to infinity of f of x dx. But this is the integral from 1/2 to 1 of, now I'm just going to write down what the function is. It's 30 times x squared times 1 minus x squared dx. And then plus the integral from 1 to infinity. Well, between 1 and infinity, f is just 0, right? It's 0 whenever it's bigger than 1 of 0 dx. And the integral of 0 is just 0, right? This disappears. So what the problem really is asking is it's asking us to compute this integral. And it looks like from the picture that the answer should be 1/2, right? If the total area under this curve is 1/2, then the area to the right of this 1/2, it looks kind of symmetric, right? So we'd expect half of the area to be over here. So let's compute this and see if it actually works, if we actually get 1/2 the area. Okay, so we have the integral from 1/2 to 1 of 30x squared times 1 minus x squared dx. The easiest way to do this is to just expand out the integral and simplify this. So this is the integral from 1/2 to 1 of 30x squared. Well, 1 minus x squared is 1 minus 2x plus x squared dx. And now we can distribute the x squared to every term, right? So this is the integral from 1/2 to 1 of 30. We have x squared minus 2x cubed plus x to the fourth dx. Or if I want to put in the 30, well, maybe I won't put in the 30. I'll keep the 30 separate. Okay, so we know that when you have a constant, you can just move it outside the integral like this. It's multiplying by a constant, it doesn't matter. You can keep the 30 out. So now we have to take an antiderivative, right? This is the fundamental theorem of calculus. To evaluate this, we do an antiderivative, evaluate it at 1, and then evaluate it at 1/2, and see what happens. So what we're going to get is 30, and then the antiderivative, well, x squared goes to 1/3 x cubed. 2x cubed goes to 2 times 1/4 x to the fourth, and then x to the fourth goes to 1/5 x to the fifth. And this is all evaluated from 1/2 to 1. Okay. So maybe we can, let me just combine this all together. So the 30 times 1/3, this is 10x cubed, right? That's the 30 times 1/3. 30 times 2 times 1/4 is minus 15x to the fourth. And then 30 times 1/5 is going to be plus 6x to the fifth, all still evaluated from 1/2 to 1. Okay. And now we write this down. This is 10 times 1 cubed minus 15 times 1 to the fourth plus 6 times 1 to the fifth, and then minus 10 times 1/2 cubed minus 15 times 1/2 to the fourth, and then plus 6 times 1/2 to the fifth. We subtract this all off. So I've run out of space, so let me just try to write down what this is going to be. All of these are 1, so this is just 10 minus 15 plus 6, so that's going to be equal to 1 over here. Maybe I'll put that in red. So that's going to be equal to 1. 10 minus 15 plus 6 is 1. And what is this? This is 10/8 minus 15/16 plus 6 over 32. So let me just do that on a calculator quickly because not that interesting. So 10/8 minus 15/16 plus 6/32 is exactly 1/2. So this over here turns out to be exactly 1/2. And so for the final results, we get 1 minus 1/2, which is 1/2. So our final result, unfortunately, I've run out of space here, but the final result is going to be 1/2. Okay. So it turns out that the probability that this random variable is at least 1/2 is exactly 1/2. What we get is that half of the area of this curve lies to the right of 1/2, and half of the area under the curve lies to the left of 1/2. Okay? And the way we figured that out is just by using the formula and taking the integral. Normally, we'd go from 1/2 to infinity, but because the function's equal to 0 once you get bigger than 1, you don't really have to go all the way to infinity. It's good enough to just go all the way to 1. Places where the function is 0, there's no area. So we don't need to take this part into account because it has no area. So we just go from 1/2 to 1, and this just becomes an integral of a polynomial, and we figure out the polynomial by using the distributive property to simplify it until we get an expression like this. Okay, so there's a bit of algebra that goes into it. But in the end, you're just evaluating this integral, and you just have to do it term by term, simplify it until you can't simplify it anymore, and then punch in 1 and punch in 1/2. Okay. Any questions about this?
Yeah, yes, sir. Good afternoon,
Yes.
sir.
Prince.
Yeah. So thank you so much for for the displacement of this equation. But my
Mhm.
concern have been June to what will have the solution set. So what will be the solution set? Because here it says 0 is less than or equal to x and x is less than or equal to 1. So what will be the solution set for x value?
Well, there's no solution set. I mean, I think by solution set, you mean when are you setting, if you set this equal to 0, could you solve that? And that's fine. But the point is, you're not trying to solve an equation f of x equals 0. That's not really part of this problem, right? The problem is asking what is this probability that that this random variable is greater than 1/2. And the way we describe these probability density functions, this is just giving you a curve. You don't really care where the curve hits the x-axis. I mean, in this case, if you want to see where this is equal to 0, it's equal when x is equal to 0, and it's equal to 0 when x is equal to 1, right? Because that makes 0 makes this vanish, and 1 makes this vanish. So you can see that's why the graph hits the x-axis at 0 and also at 1, right? But all that I'm doing here is I'm defining this function. It's a piecewise defined function. So I'm saying if x is between 0 and 1, I use this formula. If x is not between 0 and 1, I use this formula. I use just 0. So that's why I drew this graph, right? Because if I actually drew the graph of just 30 times x squared times 1 minus x squared, it would go up like this, but then it would come back up over here and it would come back up over here. But what I'm saying is actually when I'm not between 0 and 1, I'm just defining the function to be 0. Okay? So that makes the total area under the curve equal to 1, which is what you need to have a probability density function. You need the total area to be 1 because then the different partial areas like this represent the different probabilities of your variable lying in a certain range. So the probability that you're between 1/2 and 1 here represents 1/2 because between 1/2 and 1 is half of the area. And that's what we figured out here by using the integral. Does that make some sense? I don't know if I answered your question.
Yeah. Go along.
Okay. Okay. Did I answer the question?
Yes, sir. Yeah.
Okay,
I
great.
get in there. Yeah.
Okay, good.
Yeah.
Okay, other questions? Okay. Okay. Um, okay, let's go to the next problem. So the next problem is we're going to consider this function. So g of x is going to be cx squared from 0 to x to 2. This c is some constant that we haven't identified, and it's 0 otherwise. And the question is, what value of c makes f into a probability density function? So what do we have here? Let's draw this again. Here's 0, here's 2, and we have cx squared. It's going to look something like x squared, like that part of a parabola, but only between 0 and 2, right? And everywhere else, the function is just equal to 0. And everywhere else, the function's just equal to 0. So we want to know what value of c is going to make f a probability density function. And remember, to be a probability density function, what we need is that this area has to be equal to 1. Okay. So can we set up an equation? Like the question is now asking us, let's solve for c. You know, this graph is y equals cx squared. Can we find the correct value of c that makes this area equal to 1? So how can we set up an equation that's going to give us the correct value of c? Okay. Well, what we want the area to be 1. Remember, the area is the area under the curve, and that corresponds to the integral, right? So we want to set integral from 0 to 2 of this function, cx squared dx. We set this equal to 1, right? Because this here is the area. Okay? And now our c is a constant, so we can use this to solve for c. Right? What's the antiderivative of cx squared? Well, we know an antiderivative of x squared is 1/3 x cubed, right? So this is c times 1/3 x cubed evaluated from 0 to 2, which we punch in 2. That's so c over 3 times 2 cubed, and then minus, we punch in 0, c over 3 times 0 cubed, right? We punch in the 2 for x, and then we punch in the 0 for x. And we want that this equals 1, right? We want that this equals 1. And now it's just algebra. Now we can solve this. So this is saying c times 8 over 3 minus, well, this is all 0 equals 1. And that gives us, so sorry, not equals. That should be a arrow. So c times 8 over 3 minus 0 is equal to 1. So that means c is going to be equal to 3/8. So that's what we want to solve. Okay, William. Okay, so this is it. So this is the problem. So this is a little simpler than the other one. It's just saying this constant needs to be 3/8 in order to make it a probability density function. In order to make the area under the curve equal to 1, we have to solve for this constant c, and that's going to give us 3/8. Okay. Okay, so you just set up the equation that the area equals 1, and then by evaluating this integral, you can solve for c. Okay, and using this algebra, we get c times 8/3 minus 0 equals 1, and solving that for c gives us 3/8. Okay, because we multiply both sides by 3/8. All right, any questions on this? Okay, all right, no questions? Good. Okay, so homework exercise 3. So suppose that g of x represents a random variable x with the value of c that we found in question 2 above. So we're just talking about this previous function, but now with c equals 3/8, right? So this is, g of x equals 3/8 times x squared for x between 0 and 2, and 0 otherwise. And now the question is, what is the probability that our random variable, which could, in theory, take any values between 0 and 2, what's the probability that it actually takes values between 1 and 2? Okay, so for this is our straightforward. How do you do the probability that x lies between 1 and 2? Well, we seek the integral from 1 to 2 of g of x dx. This is what we need to figure out. And so now we just do this, right? So this is the integral from 1 to 2 of 3/8 x squared dx, which is equal to, well, 3/8 times 1/3 x cubed, right? That's the antiderivative of x squared is 1/3 x cubed. And we evaluate that from 1 to 2. And, well, the 3's cancel out. So this is just 1/8 x cubed evaluated from 1 to 2. And that's equal to 1/8 times 2 cubed minus 1/8 times 1 cubed. And this turns out to be 8/8 minus 1/8, which gives a final answer of 7/8. This tells us that the probability that this x lies between 1 and 2 is going to be 7/8. Okay. And what does this mean visually? It means that if we go back to our graph on the previous page, if we look between 1 and 2, so if this is 1 over here on the x-axis, and we look at the area over here, the area between 1 and 2, the green area should be equal to 7/8. Right? So the total area under the curve is 1. We want to know what's the proportion between 1 and 2. That represents the probability that this variable is between 1 and 2. That proportion is 7/8. Okay, so it's most of the area under the curve. It's 7/8 over here. It's only 1/8 over here between 0 and 1, right? Because what this graph is telling us, remember, the higher the PDF is, that's telling you that your variable is more likely to be in that range. So it's more likely in this situation that your variable takes a value between 1 and 2 than that it takes a value between 0 and 1. Okay.
Yeah, sure. Yeah,
Yes,
hello.
question.
Yeah, yeah. That flip to the next sheet where we are first. That
Hmm.
flip to the next sheet where we solve that problem. We have a 7 or 8. That flip there. Let me see something. Okay, right here. Yeah. We have a have I got it 8 1 over 8 s cubed. And where do we get a value of x from
Well,
before
that's
we
what
keep
this
it there?
notation means, right? We're looking for where the value lies between 1 and 2, which means that when you integrate, you take these values 1 and 2 over here. And so our notation here is that you find an antiderivative and then you're writing down these same values, 1 and 2, and 1 and 2 over here. And what that
Oh,
means
okay.
is that we first plug in the 2 and then we plug in the 1 and you subtract. That's what the fundamental theorem of calculus tells us. It says
Yes,
evaluate it
yes.
using 2 for x and then evaluate using 1 for x and then subtract. So that's why we have the 2 here and then the 1 over here.
Oh, okay, okay, okay. It's understood. Thank you.
Okay, great. Other questions? Okay. Okay, so that's all that we'll do about probability today. We're going to be dealing with a new topic for the rest of today that I think will be interesting. So, what we're having, just like last week, was a brief introduction to probability, although there's a lot more to say. This week is a brief introduction to differential equations, even though there's a lot more to say about it than what we're going to do today. So, first, I want to talk about, what is a differential equation? Well, everybody here knows what a standard equation is, right? You're given an equation involving some functions of x, and the goal is to solve for values of x that make the equality true. So for a standard equation, you have something like x squared plus 9 equals 13, and you're trying to find the values of x that make the statement true. So for a simple equation like this, we know that we can subtract 9 from both sides, and you get x squared equals 4. And that means the solutions are going to be x equals 2 and x equals minus 2, right? This is a standard, what's sometimes called an algebraic equation. Okay? So you're given something in terms of x, and you're trying to solve for the correct value of x. That's what a standard equation is. Now, a differential equation is a little different. A differential equation, instead of trying to figure out values for a variable x, you're trying to figure out what a function is that satisfies certain properties. So the answer to a differential equation is not a number or a set of numbers, it's a function. So what happens is you're given an equation involving y and x and maybe some derivatives of y, and you want to figure out what functions y make that equation true. And now I claim that you've already solved differential equations this semester. I didn't call them differential equations, but that's what they were. You already solved it. So specifically, anytime I've asked you to find an antiderivative, you're solving a differential equation. So, we found the antiderivative of x squared. We know that the antiderivative of x squared is 1/3 x cubed, or, 1/3 x cubed plus a constant. Well, what's another way of saying this? What does it mean to find an antiderivative of x squared? What we're really trying to do is we're trying to say solve for y. And we have the equation dy dx equals x squared. We're trying to solve the equation, what is a function y so that its derivative with respect to x is equal to x squared. This is what it means to find an antiderivative for x squared. We have an equation like this. It's called a differential equation because there's a derivative going on in the equation. And we want to know what is the value of y that makes this true. And it's not, the answer is not going to be y equals 3 or y equals 5. It's not going to be a number. If it's a number, dy dx just equals 0. It's not the same as x squared. But the point is that y should be some function of x so that when you take the derivative of that function, you get x squared. That's what makes this a differential equation. So in this case, the differential equation has lots of solutions, and all of the solutions are of the form y equals 1/3 x cubed plus c, where c is some constant. Okay? Because if I punch in y equals 1/3 x cubed plus c into this equation, then the equation becomes true. I take the derivative, I get x squared, and I get x squared equals x squared, so that's true. Okay, so when you have a differential equation like this, you have some y's and x's, and what you're trying to do is solve for y as a function of x, not as a number. You're trying to find the correct function that when you punch it into the equation makes it true. Okay, and certainly, right, anytime that your equation, anytime you're trying to find an antiderivative, this is what you have. If you want an antiderivative of x squared, you're solving dy dx equals x squared. If you want an antiderivative of cosine of x, you solve dy dx equals cosine of x, and so on. So these are all, anytime you're finding an antiderivative, you're solving a particular type of differential equation. Okay, any questions on this? Okay, so let's talk about a very useful differential equation that has lots of applications. So first of all, if you want to follow in the textbook, today's material is all in section 5.5. So you can look at it there in 5.5. Okay. So if you recall, this function e to the x is its own derivative. We showed this, right? That the derivative of e to the x is e to the x. And so another way of phrasing that is that if I take the function y equals e to the x, that this is a solution to the differential equation dy dx equals y, right? Because what that says is if I plug in y equals e to the x, what do I get? I get that the derivative of e to the x, that's the left-hand side here.
Yes, so which means the entire thing will just be e to the x.
Exactly, right? So I'm plugging in y equals e to the x. So everywhere I see a y, I replace it with e to the x. And then what this equation tells me is that the derivative of e to the x equals e to the x, which is certainly true, right? So this is true.
So which means, for example, if you have a function to be the y and y equal e to the 2s or e to the 3s, the function will still be the same thing. Now, if you differentiate e to the 3s, well, you get 3 e to the 3x.
Mm-hmm. Yeah, so that would not be a solution to this differential equation because you would have, because dy dx wouldn't be the same as y. It would actually be multiplied by 3.
Yeah, sure.
Right. But this is what we mean by solving this differential equation. We can see that what this differential equation is really asking for is it's saying, give me a function y whose derivative equals itself. That's what this equation says. I want the derivative of y to be equal to y. So can we think of some other functions that are also solutions to this differential equation? So we know y equals e to the x works. Its derivative is equal to itself. Can we think of other functions whose derivatives are also themselves? There aren't that many, but there are some more. Can anybody come up with another example of a function that when you take its derivative, you just get itself back?
Yeah.
Yes, Enoch? So any other ideas?
Hello?
Hello, yeah, Enoch?
Yeah, I wanted for her to try. Is that 2e to the 2x or 1 over 2e to the 2x? Yeah,
2e to the 2x is still, when we take the derivative, it's going to give us 4e to the 2x. So let's
Oh,
actually
wow.
make it just a little bit simpler,
Okay.
right? So what if we just have 2 times e to the x, right? So then dy
Yeah,
dx,
sure. That's it. That's
right,
it. Good.
is
Yeah,
also
it will
2e
work.
to the x.
Okay, so which means if it is in this form, like if you get 2e to the 2x, 3e to the 3x, 4e to the 4x, and let's say or 2e to the x, 3e
Right.
to the x, 4e to the x. Yeah, they will still
Exactly.
be the same.
So in
Or
general, we
constant.
can take c e to the x, right, for any constant c. Right? For any constant c, right? Because if I take the derivative of c e to the x, I get c e to the x again, right? The constant just stays the constant, and e to the x, the derivative is e to the x. So if I take the derivative of c e to the x, I get c e to the x. So that turns out that that's going to be a solution to this differential equation, right? Because the differential equation is saying it's looking for a function where the derivative of that function equals the function itself, right? So c e to the x is going to work no matter what your constant is. In particular, if your constant is 0, if c is 0, that gives you 0 e to the x, which is just the same as 0. But 0 definitely works. The derivative of 0 is 0, right? So that also works as a solution here. Okay? So it turns out that a solution to this differential equation can be given by any constant that you want times e to the x. If so, it solves the differential equation dy dx equals y, because that equation's asking for a function where the derivative is equal to itself. All right, any questions?
Yeah, sure.
Yes, Prince.
Yeah, my question is, can negative be used to get the true set of the solution?
Yeah, negatives are fine because any constant c is fine. So it can be either positive or negative. So negative e to the x is also okay, and its derivative
Okay,
will be negative e to the x. So any constant at all, positive or negative.
okay, thank you.
You're welcome. Other questions?
Hello?
Hello, yes. Rush?
Yeah. Hello, sir. So in case you're having like y equals to the constant, which is the constant x plus the constant, let's say you have two constants, right?
Mm-hmm.
Then you have let's assume you have y equals to, which is c1x plus c2 e raised to the power negative x. So it has to, we can still apply that, right?
Well, yeah, but you can't have e to the negative. It's not going to solve this equation if you've got an e to the negative x, right? What's the problem is that, right, d dx of e to the negative x, we saw this last time, it's negative e to the negative x, right?
Sure.
So the derivative is not equal to itself. It's equal to the negative of itself. And so if you have any e to the minus x's in your solution, when you take the derivative, it's not going to stay the same. So in fact, you really don't want a constant with an e to the minus x, right? You really only want e to the positive x because that's the only thing that actually stays the same when you take the derivative.
Okay,
Okay, does that make sense?
okay, thanks.
Great, you're welcome. Okay. Okay. All right. So this is a simple differential equation, but it's not as easy as this because it involves a y on both sides. So this is just dy dx equals x squared. That's just taking an antiderivative of x squared. But here we have dy dx equals y, and that really involves thinking. You got to think, okay, what functions do we know whose derivative is equal to themselves? And in fact, it turns out these are the only functions. Only c e to the x works. I'm not going to prove that, but It is true. But in general, we can see that any c to the e to the x does work. Okay, these all satisfy the differential equation. Okay, so what's another differential equation? So we've seen that y equals c e to the x is a solution to this differential equation, dy dx equals y, for any constant c. Now, let's make the equation a little bit more complicated. Let's write dy dx equals ky, where k is some other constant. So we want to know what's a function, what is this asking in English? This is saying find a function y whose derivative is k times itself. Right, that's what this is saying. It's saying find a function y where the derivative of y, that's the left-hand side, is equal to k times y. That's the right-hand side, so k times itself. So can we think of a function, if I give you some constant k, can you think of a function, and Enoch, this is going to be related to what you said earlier, can you think of a function where when you take the derivative, what that actually does is it multiplies the function by k?
That was?
Yep. Robert?
Yeah, what if the function e raised to the 2x, when you differentiate that, you will get 2e raised to the 2x.
Right, so that's great. So that will work if k is equal to 2. And so what do you do for a general k? Instead of e to the 2x, just... Right, so the e to the 2x works if k is equal to 2. So for general k, we can write e to the kx. Right, what happens when we take the derivative of e to the kx? Right, well, we know by the chain rule, it's e to the function of x. So the derivative is just e to the same function, e to the kx, but because of the chain rule, we have to multiply by the derivative of kx, right? So by d dx of kx, but the derivative of kx is just k when k is a constant. So this is equal to k times e to the kx. And this works, right? We have a function here that when we take its derivative, we get k times the function, right? So if this is y, we get here k times y. Okay, so e to the kx is a solution to this differential equation when k is a constant, right? We have dy dx equals ky. That's a solution when k is a constant. And more generally, so in general, you can also take y equals not just e to the kx, but you can multiply it by any constant. I'll call that constant capital C. So if I take c e to the kx for any c, then when I take the derivative, right, dy dx, well, e to the kx goes to k e to the kx. So if I multiply the function by c, it also multiplies the derivative by c, and this is going to give me ck e to the kx. So which solves the equation. Okay. All right. So the general solution for this differential equation is in this form. So if I have dy dx equals 2y, then the general solution is y equals c times e to the 2x. If I have dy dx equals 5y, then I get c times e to the 5x is the general solution for any constant c. Dy dx equals 1000y, I get c times e to the 1000x is going to be a solution. Okay, so as you see, differential equations can get harder and harder, and they can get extremely hard, and we're not going to deal with hard differential equations in this class. Basically, this is the only differential equation we're going to look at. But this differential equation has two good properties. So one is that we can solve it without too much effort. So this works as a solution. And the other is that it turns out to be very useful for modeling things in science. Okay, so this differential equation dy dx equals ky, we'll talk about on the next slide what it means in real life. But before we talk about what it means, we can at least verify that if I take y equals any constant times e to the kx, it's going to satisfy this equation, right? Because these are all functions such that if you take the derivative, it's the same as multiplying the function by k, right? C e to the kx becomes c k e to the kx. It gets multiplied by k when you take the derivative. Okay, that's what we're trying to do. We're trying to find a function k whose derivative is k times itself. That's exactly what you get with c e to the kx. Okay. All right. Any question? Okay, give me 1 second. I'm just going to get a little water and then we'll move on. Okay. Okay. So what does this mean? So let's look more at this differential equation, dy dx equals ky. So remember what what a derivative means. What have we been studying this whole year? What is a derivative fundamentally? A derivative is a rate of change, right? So this is saying that the rate of change of y with respect to x, and sometimes this is actually better, maybe even easier to understand if we call this t for time instead of x. This is saying that the rate of change of y with respect to time is proportional to the value of y, right? This is a proportion, right? We're saying that y times a constant equals the rate of change of y. So another way of saying is that the bigger y is, the bigger the rate of change of y is, right? If I double y, I also double dy dt here, right? Because they're proportional to each other. Okay? So you want something that the bigger it gets, the faster it grows. Okay? And so what we say is that a quantity that satisfies this differential equation is said to experience exponential growth if k is positive, or exponential decay if k is negative. And this constant k is called the relative growth rate, right? I mean, why do we call it exponential? Because we know that the solution is an exponential. We know that the solution is y equals c times e to the k. I'll call it t now for time instead of x. But it's the same thing whether it's t or x, right? So this is what we have. And notice that if k is positive, this is an increasing function of t because you're getting an increasing exponent. And if t is negative, sorry, if k is negative, then this is a decreasing function of t because the exponent gets more and more negative. So this will level off at 0 if k is negative. When t goes to infinity, this whole thing goes to 0. Okay? And so it turns out that this exponential growth and decay is frequently used to model population growth. It models radioactivity, it models compound interest, and it models heating and cooling via Newton's law. Okay, so not bad for one differential equation, that it actually models all of these different things from different fields of knowledge. Okay, and we're going to do examples for all of these. Okay, but remember, this is the solution for the equation in terms of an exponential. And what's the main property that this solution has? Oh, wait, sorry. One second. Sorry. Okay. Okay. No. Yeah, sorry. Did I close the file? Yes.
Hello, sir.
Yep. Sorry. Hello. Yes, Rush?
So this is common like the algebra constant what they use. I think almost like those that are doing 304 where you have the constants, there you get many constants applying, right?
Yeah. So every different constant is a different proportion. So I will see, for instance, if you're trying to measure radioactive decay, depending on the half-life of the substance, you're going to have a different constant.
Okay.
Yeah. So the constant depends on what physical situation you're actually looking at. Okay. So the good news is we solved this equation once, which means we don't have to solve it again, right? We have this solution. And so the questions are, well, we'll see how these questions work. But the idea is if you have anything, any physical process where the change is proportional to the amount of the substance that you have, and that substance could be population of a bacteria or the amount of radioactive material or the amount of money in a bank account, anything like that, anything that grows proportionally to how much there is going to satisfy an equation like this. And the solution will always be exponential growth. So let's look at an example. Population growth. Okay, so a bacterial culture initially consists of 100 cells, and it grows at a rate proportional to its size. This means exponential growth, right? So after an hour, the population has increased to 420 cells. So it's a four-part question. Find the relative growth rate, an expression for the number of bacteria after 3 hours, the rate of growth after 3 hours, and the number of hours until the population hits 10,000. Okay, so it's a lot of things that we're asked to find from not very much information. And so the key idea is that we know that when you grow at a rate proportional to its size, that means that what we have is exponential growth. Which means we have this formula from before. If I take y to be, let y of t be equal to the population of bacteria, after t hours, then we have that y is equal to c e to the kt for some c and k, right? That's what exponential growth says. And when you have something like this, once we know what c and k are, then we'll be able to solve all of the parts of this question. Okay. And in fact, the first part asks us to find k. Remember, k is the relative growth rate. So we have to find k. So we have this equation, y equals CEKT, and we need to solve it for c and k. Okay, e is a number. We don't need to solve for e, and t is just our independent variable. It's time. Okay, so we don't solve for t when trying to find out what the actual function is. We need to know, just because it has exponential growth, there's still two parameters that you might need to figure out. You need to figure out c, and you need to figure out k. So what do we know? Well, we know that it initially consists of 100 cells. So we know that y of 0 is equal to 100. Right? That's this initially consists of 100 cells. So the population after 0 hours is 100. So what that tells us, so if we punch this in for t and this in for y, what we end up getting is that 100 is equal to c times e to the k times 0, which is just equal to c, right? Because k times 0 is 0. This whole thing here is 1. Okay, so that's good. So this tells us that c equals 100. Great. So we've solved for one of the parameters. Now we just have to figure out k. Well, k says after an hour, the population has increased to 420. So what that tells us is that y of 1 is equal to 420. So that, again, we have our function. So that's saying if we punch in t equals 1, we get that y equals 420. So this tells us that 420 equals c times e to the k times 1. But c is already 100, so that's 100 e to the k. Or in other words, 420 divided by 100, so 4.2 is equal to e to the k. And the way we solve this is another way of saying that k is equal to the natural logarithm of 4.2. That I need to use a calculator for. So the natural logarithm of 4.2 is about 1.435. So this is the answer for part A. The relative growth rate is 1.435. That's our k. And now we know that the function is y equals 100 times e to the 1.435 t. Right? And the point is, once we know this, we can answer the rest of the question. Okay, so the key with all these exponential growth questions is first, try to figure out what the function is. You know it will always have the form c e to the kt, but to know what's the right value of c and what's the right value of k, you've got to use the information in the problem. So the information in the problem tells you that y of 0 equals 100 and y of 1 equals 420. Using that information, you can figure out the values of c and k. We use this to figure out c equals 100 and k equals 1.435. Okay. So before we do parts B, C, and D, any questions about how we got here? So this is the answer to part A over here is 1.435. Any questions as to how we got this equation for how the number of bacteria grows with time? It's 100 times e to the 1.435 t.
Yeah, that I think it's well understood to me. So get more for
Okay,
me, well
great.
understood.
Okay, so B says, what's an expression for the number of bacteria after 3 hours? That we just need to punch in t equals 3, right? So part B, we just want 100 times e to the 1.435 times 3. So what's that going to equal? Let me just use a calculator. 100 times e to the 1.435 times 3. That's going to give us about 7,407 bacteria. So it grows very quickly, right? 100 goes up to 420, and then 420 goes all the way up to 7,407. The rate of growth after 3 hours, that's C. Well, we know dy dt equals ky. Well, our y is the amount of bacteria, that's 7,407, and k is 1.435, right? So this ends up giving us 1.435 times 7,407, which is equal to 1.435, which is equal to about 10,629 bacteria per hour. Sorry that the writing got a little bit small, but that's the answer for C. Because the rate of growth is exactly this ky. That's what's equal to dy dt, which is the rate of growth. So the rate of growth is going to be the amount of bacteria times this constant k. So that's 7,407 times 1.435. And then D says, what is the number of hours until the population hits 10,000? That's just solving this equation for T if you have y equals 10,000. So I'll just write that on another page. Remember, we have y equals 100 times e to the 1.435t. And we want to solve, when does y equal 10,000? Well, we just need to solve for t. Right, so we have 10,000 equals 100 times e to the 1.435t. We can divide both sides by 100, and that will leave us with 100 equals e to the 1.435t. And now what we do is we take ln of both sides. Ln is how we eliminate e from an equation. Ln of both sides gives us that ln of 100 equals, well, natural log of e to the 1.435t. That's saying, what do you need to raise e to get e to the 1.435t? The answer is 1.435t. So the ln and the e cancel each other out because they're inverse functions. 1.435t, sorry, it says that. And so what that's going to tell us is that t is equal to ln of 100 divided by 1.435. And that's going to be, let me write that down. So ln of 100 divided by 1.435 is going to be about 3.209 hours. Okay, so at 3 hours, remember it got to 7,400 bacteria. To get to 10,000, it means a little bit more time. It needs about another 12 minutes. Okay, to get to 3.209 hours, and I'm closer to 13 minutes. Okay. Okay, any questions on this?
Peterosa.
Yes, Rush?
The 4.2, the 4.2 that would divide by the 100, right?
Right, so we
They
did, I
will have
had 10,000, you mean over here?
the starting point at the
Yeah.
back.
Over here, the 4.2 over here? Yes. So we divided by 100, right? So 420 equals 100 times e to the k. So we divide by 100 on both sides. That gives us 4.2 equals e to the k. And then when we take the logarithm, we get k equals natural log of 4.2.
Thank you.
Okay, you're welcome. Okay. So we're going to have a few more examples like this. Okay, but the key is always the same, is you write down this general form. You want to know what is C, what is K, and once you know what C and K are, you can solve for anything. Okay, so this is an example involving population growth. Okay, and this is a pretty good model for population growth, at least in the early stages of a population. Okay. So let me just remark, yeah, so what is this general procedure? When you're solving an exponential growth or decay problem, you know that the equation giving the desired quantity in terms of time is always y equals c e to the kt for some constant c and k. The key to the problem is always figure out what c and k are. Once you know this, you can solve for the quantities y and t in terms of each other. And you will always be given at least two pieces of information in the problem, because you need two pieces of information in order to solve for the two variables c and k. Right? In this problem, we were given two pieces of information. We said that it starts with 100 cells, and after an hour, it's increased to 420 cells. So that's two pieces of information. And we needed to use both of them to solve for these variables c and k. Okay, so let's look at another example. So radioactive decay and half-life. Okay, so in general, if you have a radioactive substance, then the quantity of the radioactive material in a substance always experiences exponential decay. This is called radioactive decay in physics. And if you have a radioactive substance, it comes with something called a half-life. So the half-life of the substance is how long it takes for half of the radioactive material in the substance to decay, to get rid of its radiation. And different substances have very different half-lives. So for instance, the half-life of something called carbon-14 is 5,730 years. So if you have a sample of carbon-14, it takes 5,730 years for half of the radiation to decay. Right? So that's a long time. It's actually used to date fossils and things like that. They can see how much carbon-14 there is in the sample. Other things are much faster. So the half-life of uranium-234 is about 1 millisecond. So in 1/1000th of a second, half the radiation is already gone, right? So the radiation leaves very, very quickly for uranium-234. Okay, Rosh, thank you for letting me know. And so if you're interested in the physics in radioactive nuclear physics, then if you look at the Wikipedia article, list of radioactive nuclides by half-life, it gives you basically every radioactive atom that there is and what its half-life is. It's a super long list, but you can look up anything you want. So that's where I found the carbon-14, and that's where I found the uranium-234. Okay. A list of radioactive nuclides by half-life. It's a pretty comprehensive list in Wikipedia. Okay. So how do we do a problem with radioactive decay and half-life? So remember, radioactive substance is exponential decay. This is how it works. It does undergo exponential decay. So the rate at which it decays is proportional to the amount of substance that there is. Okay, this is how radioactive stuff works. So the question is, so here we have the half-life of radium-226 is 1,590 years. A sample of radium-226 has mass 100 milligrams. We want to find a formula for the mass that remains after T years. And when will the mass be reduced to 30 milligrams? Okay, so it's really two questions, right? The first is find a formula for the mass that remains after T years. And the second is when will the mass be reduced to 30 milligrams? Okay, so what do? We always start with y equals c e to the kt, right? This is our exponential decay equation. Right? This is our exponential decay. We always start with this. Now, what's our information? Well, we know that a sample has a mass of 100 milligrams. So that's right now. So the sample of radium-226 has mass 100 milligrams. So we know that at time 0, y of 0 is equal to 100. Right? This is saying that if the sample today is 100 milligrams. So punching that into this formula, that tells us that 100 is equal to c times e to the k times 0. Right? This is what we plug in. Our 0 is t and our 100 is y. So again, e to the k times 0 is just 1. That tells us that that's equal to 100 times c e to the 0. Sorry, 100 equals c e to the 0, which tells us that 100 is equal to c. Okay, so this allows us to solve for C. C is what we start with. Okay. And so what's the other thing? Well, we also know that the half-life is 1,590 years. So we also know that the amount of the substance that's left after 1,590 years is, well, if we started with 100 milligrams, then after 1,590 years, we have 50 milligrams, right? It's going to be half of 100. That's what the half-life means. It means half the substance goes away and decays into other isotopes. Right, so this is the other thing that we know. What does this mean in terms of equations? This tells us that 50 is equal to C times e to the k times 1590. And again, this is our T, and this is our Y. And in fact, our C we know is 100. So this tells us that 50 equals 100 times e to the 1590k. Or in other words, we can divide both sides by 100, so we get 50 over 100 equals e to the 1590k. That's just 1/2, right? 1/2 equals e to the 1590k. And now we can take ln of both sides. That says that ln of 1/2 equals 1590k. That tells us that k is equal to ln of 1/2 divided by 1590. And now I can use a calculator to solve this. So ln of 1/2 divided by 1590, this gives us that k is equal to 0.000436. Write it like that. Okay. So the amount that remains after, so find a formula for the mass that remains after t years. It's just asking us to write down this function. So we have that y. Sorry, yes, Princeton?
Yeah, my concern about due to this 50 that we got here.
Mm-hmm. So over here.
Yeah, where we got Y, parenthesis will be 1590 equal to 50. So I don't know how we got the 50.
So yeah, so that's important. So the half-life is 1,590 years. So remember what half-life means. It means after 1,590 years, half the sample is left. So we started with 100 milligrams. So at time 0, we have 100. What the half-life says is that 1,590 years later, you have half of what you started with. So half of our 100 is 50.
Oh, okay.
That's it. Yeah, so it's just because it's one half-life, which means we've lost half the substance. Right, so maybe I should say this 50, right? The point of this 50 is that it's equal to 1/2 times 100. It means half of the substance is gone. Okay, so writing this all out, we have y equals 100 times e to the 0.000436t. Right, this is the answer to the first question. And now the second question says, when will the mass be reduced to 30 milligrams? So that means we just are punching in 30 for y and solving for t. So for the second part, we just want to solve 30 equals 100 times e to the 0.000436t. Okay. So right, because we know when do we get 30, we need to know at what time t do we get 30. And this t, I want to make sure this t is in the exponent here. T is up there in the exponent. So let me go solve this equation on the next page. Okay, so we have 30 equals 100 times e to the 0.000, how many zeros? 40. Oh, wait, is there an extra zero? No, that's right. Okay. Okay, so 0.00436t. I can divide both sides by 100, so I get 0.3 equals e to the 0.0000436t, right? Just divided 30 by 100 to get 0.3. And now I can take ln's, so ln of 0.3, oh, sorry, this should be in negative. These are negatives. Sorry, this is k equals negative here. Everything was in negative. Sorry, negative, negative, negative. Okay, negative. So ln of 0.3 equals, the ln cancels out the e, so we get negative 0.000436t, and this gives us that t is equal to ln of 0.3 divided by negative 0.000436, and for this we use the calculator. So let's see what we got. ln of 0.3 divided by negative 0.000436, and that's going to tell us that it's about 2,761 years. Okay, so it takes 1,590 years for half of it to decay, so to decay to 50 milligrams. To get all the way down to 30 milligrams takes longer. It takes 2,761 years. Okay? But just from this information about half-life, we're able to figure out, exactly how long it will take for something like this to happen. And again, the key is we know the equation that governs everything is going to look like this. And so we just need the information, what is C and what is K. That's all that we need to know. Okay, so any questions on this? All right, any questions anywhere?
Yes, Data over.
Yes, Princeton.
Yes. So looking at the KT, and we are representing the 1590 for T, right?
Right, because 1,590 years.
For T. Then how can we are now substitute the T now with 1590, and then the answering we got 2761 as T equal to 2761.
Because 1,590 is a special T. It's a T that is telling you this is how long you need for half the substance to decay. So if you start with 100 milligrams, then 1,590 is how long it takes to get 50 milligrams. So we're using that information to solve for K. The whole point of the 1590 is to ultimately let us solve for this K, which is minus 0.000436. So once we know what that K is, now we know what the real equation for Y is. It's 100 times e to the minus 0.000436t. Once you know this equation, you don't care about the 1590 anymore. This now tells you how to relate y and t for any values at all. 1590 is just this special value that tells you when half of the substance is gone. But now the question says, when will the mass be reduced to 30 milligrams? So to get 30 milligrams, I want to know when is y equal to 30. So I'm just going to substitute 30 for y and solve for whatever t is going to be. It's not going to be 1590, right? Because after 1590 years, I have 50 milligrams left. I want to know when will I have 30 milligrams. That's going to take longer than 1590 years.
So that means the value now is negative 0.000436.
That's the value of K. That's the relative decay factor. Sorry, I lost you. Do you have anything? Right. And so then when we solve this equation, we actually got 2,761 years, which makes sense because it should be longer than 1,590 years because we need enough time to get down to 30, not just to get down to 50. Is that okay, Princeton?
Yeah, I
Okay.
think, yeah.
Okay, great.
Thank you.
All right, you're welcome. Other questions?
So another thing here is the E now represent the RN, which is the natural law.
Mm-hmm.
So the letter E now represent the natural law, right?
Well, the letter E is canceled out by the natural log. So when you want to
Okay.
solve an equation that involves an E, the way you cancel the E from the equation is by taking natural log of both sides, right? So what I'm doing is I'm taking natural log of the left and natural log of the right. And when I take natural log, it cancels out the E, and I'm left with just the exponent here. I'm left with just
Yeah.
minus 0.000436t.
Okay.
Yeah, you're welcome. Yeah, ln, yeah, natural log. All right, any questions, further questions on this? Okay. Okay, great. Okay, so let's go on. One more example. This will probably be the last one. I think we'll have to hold off on the compound interest until next time. We'll do the compound interest next time. Okay, so Newton's law of heating and cooling. So let's say that T of T is the temperature of an object at time T. And suppose that the surrounding temperature, we say, we'll call it Ts, S for surrounding. So what does Newton's law of heating and cooling say? It says that there's a constant K such that the rate of change of the temperature with respect to time, so dt, d capital T, d lowercase t, is equal to K times the difference between the actual temperature and the surrounding temperature. So for instance, if an object is much hotter than its surrounding temperature, then it will cool quickly. If an object's only a little bit hotter than the surrounding temperature, then it's going to cool slowly. And what is the actual constant K? That depends on what the substance is. So certain things, metals, maybe cool much slower than some other things like plastic. It's going to cool much faster. So let's make a change of variables. Let me substitute y equals T minus Ts. Remember this Ts, this is the surrounding temperature. This is a constant. Okay, it's just like the temperature outside or the temperature in a freezer or something like that. Okay, so if we take y equals T minus a constant, then the derivative of y is the same thing as the derivative of t, right? Because this extra constant doesn't mean anything when it comes to derivatives. So this dy dt is the same thing as d capital T dt. They're the same, right? Because y and t are the same except for subtracting a constant. That doesn't change the derivative. So if we want to rewrite Newton's law with y instead of t, we can rewrite this dt dt is just dy dt. And k times t minus ts, this here is just y. So we get dy dt equals ky. And this is going to be, this is exactly, we have exponential, growth or decay. And here's a question. Should our k be positive or negative? So if you have an object that's much hotter than its surroundings, is the object going to get hotter or colder? If I take
Higher.
It's
It
going
will
to
be
get colder,
positive.
right? If I take a hot stew and I put it in the freezer, is the stew going to get colder or hotter?
As tea and put in freezer, it will be colder
It's going to
because
get
the
colder,
freezer
right?
maybe,
Exactly.
yeah.
So if this is, my soup temperature and this is my freezer temperature, that's the surroundings, right? So in this case, this thing is positive, right? The soup is hotter than the freezer. So the temperature of the soup is hotter than the temperature of the freezer. So this is positive. But we know that the change in temperature, this gets colder, right? So this change is negative because the soup gets colder, right? So what we see is if this is positive, this side over here is positive, or at least this y over here is positive, and the left-hand side here is negative. The only way that can be true is that this k here also has to be negative, right? Because we've got a positive quantity here and a negative quantity here. So the only way they can be equal is if you multiply by a negative quantity. So we see here is k is negative. So we have exponential decay. Okay, it's going to decay to an equilibrium. Eventually, the object gets close to the temperature of the surroundings. It approaches the temperature of the surroundings in the limit. Okay, but overall, we have the same differential equation. dy dt equals ky. You just have to have that y is equal not to the actual temperature of the object, but the difference between the temperature and the surrounding temperature. Okay, so let's close with one example for this.
Yes, yes,
Yes, no
Dada
question?
August.
Yes, before we do an example, yes, Princeton?
Yeah, I'm looking at DT or DT. I don't know what is the difference between both of them. We got the
Capital T is
uppercase and
temperature and lowercase t is time.
okay.
Yeah, that's why they're both t's. So capital T is temperature and lowercase t is time.
Okay, thank you.
Yeah. Other questions? So let's look at this with an example. Okay, so we have a bottle of water that's 72 degrees Fahrenheit, and it's placed in a refrigerator with temperature 40 degrees Fahrenheit. After half an hour, the water is cooled to 61 degrees Fahrenheit. And the question is, what is the temperature of the water after another half hour? And then how long does it take the water to cool to 50 degrees Fahrenheit? Okay, so as always, it's exponential decay, so we always have that y is equal to c times e to the kt. Always what you have. But here, y, remember, y is equal to the difference. Y is equal to the temperature of the water minus the temperature of the refrigerator. Right? Temperature of the water minus the temperature of the refrigerator. Okay, but we have the same thing. So just like every other question, we start with what do we know, and then we can try to figure out K and T. So what do we know? Placed, pulsed, placed. Okay, so we know the water is 72 degrees Fahrenheit and the temperature is 40. So at time 0, y of 0 is equal to 72 minus 40, which is equal to 32. Right? This just means at time 0, temperature is 72. Okay, right. So 32 degrees, exactly. We can write it as degrees if we want. So what do we also know? Well, after half an hour, so that's y of 1/2, the temperature is now 61 degrees. So y is 61 minus 40, that'd be 21 degrees, right? at time 1/2, temperature is 61 degrees. So y of 0 equals 32 degrees. What does that tell us? That tells us 32 is equal to c times e to the k times 0. Or in other words, c equals 32. And over here, y of 1/2 equals 21. That tells us that 21 is equal to c times e to the k times 1/2. But c we know is 32. So that's 32 e to the, I'll write 1/2 k. And so this tells us that I can divide both sides by 32. So 21 over 32 equals e to the 1/2 k. And again, we take ln of both sides. So ln of 21 over 32 equals 1/2 k. And that tells us that 2 times ln of 21 over 32 equals k. And now we can use the calculator to figure this out. So 2 times ln of 21 divided by 32 is, k is going to be equal to minus 0.8424. Let's say. Okay, sorry, your phone's about to go off. Yeah, we'll finish up in the next 5 minutes probably. Okay, so k is minus 0.84024. So now we know what c is, and we know what k is, just like we always do. So we get that y is equal to 32 times e to the minus 0.8424 t. Right, this is the function. So now we can answer the two questions. So the first question says, what is the temperature of the water after another half hour? Well, so that means 1 hour later. So the first question is asking for y of 1. That's after 1 full hour, right? So y of 1, so it's saying y of 1 is equal to 32 times e to the minus 0.8424 times 1. That's a times 1, not a 0.1, times 1. And so I can just write that down, right? So let me put that in the calculator. 32 times e to the minus 0.8424. That's going to be equal to about 13.78. But remember, that's y. 13.78 is the difference between y and 40 degrees, right? So T minus 40 degrees equals 13.78 degrees. So T is going to be 53.78 degrees. Right? That's what we get for the temperature, right? At time 1, y is 13.78, but that means the temperature of the water is actually 53.78. It's 40 degrees warmer. Remember, y is the difference between T and 40 degrees. So after an hour, the water's cooled down to 53.78 degrees. And then the question is, how long does it take the water to cool to 50 degrees? Well, remember, when the water is 50 degrees temperature, the refrigerator is 40 degrees, so that means y is 10. So we need to solve this equation for t when y is equal to 10. So I'm going to do that on the next page. So remember, if t is equal to 50 degrees, then y is equal to 50 degrees minus 40 degrees equals 10 degrees. So what we want to do is solve this equation for t, plugging in y equals 10 degrees. So solve 10 equals 32 times e to the minus 0.8424 t. It's saying 10 over 32 equals e to the minus 0.8424 t. Again, we do ln of both sides. That gives us ln of 10 over 32 equals minus 0.8424 t. Or in other words, t equals ln of 10 over 32 divided by minus 0.8424. So now again, we do this on a calculator. So we have, what is it? ln of 10 30-seconds divided by minus 0.8424. And that's going to give me about 1.38. Okay, hours. Okay, so that's how long it's going to take to get down to 50 degrees. So it takes, after half an hour, it's at 61 degrees. After a full hour, it's at 53.78 degrees. And to get all the way down to 50 degrees requires a little bit more time, requires 1.38 hours. Okay, so that's about an hour and 22 minutes or so. Sorry, not 22 minutes, like, yeah, 23 minutes. All right, any questions about this example? I mean, so the key is no matter what problem you're looking at, whether it's a Newton's law or radioactivity or population growth or anything like that, it's always the same. You always just write down the general exponential growth or decay equation, use your information to figure out what C and K are. And then once you know what C and K are, once you have this actual function, anything the question asks you, you'll be able to figure out by just either plugging in a t value and solving for y, or plugging in a y value and solving for t. Once you know how the quantity and the time are related, then you know everything about the long-term trajectory of how the substance works. Okay. All right, any questions about this? Okay, good. So if there's no questions, I think I don't want to rush compound interest, so we're gonna do this next time. Okay, I'm gonna skip compound interest for now. This will be next time. Okay, we're gonna see what exponentials have to do, exponential growth has to do with compound interest. I mean, you have exponential growth if you have infinitely quick compounding. And so here's some homework exercises. So the first one says that strontium-90 has a half-life of 28 days, and a sample has a mass of 50 milligrams initially. Find a formula for the mass remaining after T days. And how long does it take for the sample to decay to 2 milligrams? So this is a lot like our half-life example that we did today. Number 2, a bowl of hot soup is taken off the stove at a temperature of 130 degrees Fahrenheit. Temperature outside is 80 degrees Fahrenheit. 2 minutes later, the temperature of the soup is 110 degrees Fahrenheit. How long will it take the soup to cool to 100 degrees Fahrenheit? So this is a Newton's law of cooling problem, similar to the last one that we did. And number 3, bit of a challenge. A sample of tritium-3. So for the hydrogen tritium-3 for the chemists, this is hydrogen with one proton and and 2 neutrons. That's what tritium is, tritium-3. This is decayed to 90. You don't need to know this for the problem, but if you like chemistry, then this is what it is. So it's decayed to 94.5% of its original mass after 1 year. So the question is, what is its half-life? And how long will it take for the sample to decay to 20% of its original mass? Okay, so it's a lot like the other problems, but it's phrased a little bit differently. So this one might be a bit of a challenge. So we'll talk about this one next time. So these are the homework exercises. And then, so scheduling. There is no class the next 2 weeks. On May 1st, I'm going to actually be in England at a conference. And then May 8th is going to be the WITS math competition. So we're not going to have class that week because people will be busy, or at least some people will be busy. with the WITS math competition. Okay, so sorry, so May 1st. The next class, sorry, is not May 8th. The next class is on May 15th, when we'll discuss sequences and series, and we will also do compound interest. Okay. So yeah, so no class for a while. So you definitely have time to try to do these homework exercises. Hopefully, I'll get some solutions, or some proposed solutions, and we're going to move on to sequences and series, which is also part of the grade 12 curriculum at least. So we have 3 more weeks of 3 more sessions this term, and we're going to be spending them all on sequences and series. Okay, so we're going to talk about that for the last part. So, but of course, we'll review this exponential growth and decay before we move on to that. Okay, any last questions? Okay, so anybody who hasn't yet put their name in the chat, please go and do so. Hi, Aby.
Yeah, man.
Yeah. Yes, I'm not getting you so well. Hello?
Yeah.
Yes, hi.
Andrew?
Yes.
Yes. You were to the class. We shall see you after 2 weeks.
Mhm.
And we will be sure that we have the competition on the 10th.
Oh, it's going to be on the
May.
10th? Okay, so actually May 10th.
And then we want to have it on the 10th of May, because on the 15th will be the wax for the senior class. Yeah.
Okay, yeah, anytime. Yeah, you can do it anytime between the 5th and the 11th.
Class.
Yeah. Anytime May 5th to
Yeah,
11th
that one
is
want
okay.
to do. That one want to do.
Yep.
Okay. But we'll be fighting to do our registration before the 10th.
Right.
Okay. Thank you very much.
Anytime between 5 and 11 is okay. Okay. All right. Okay, anything else? On commercial vehicle. Okay, yes. Okay, no, I definitely have your record for attendance. Okay, so I'm going to stop the recording.